In this video here, we're working on finding the electric field at a point H above a rod that extends to L over 2 in one direction and minus L over 2 in the other direction. It's electric field superposition due to continuous media here because we have a continuous rod here. And in previous video, we sort of discussed the differences between discrete superposition and continuous superposition. And this is one of continuous superposition that we'll have to use calculus to get at it. So let's just get at it then. Let's see if we can find the electric field at this point right here. So what we'll do is we have to discretize the problem as best we can. So we're going to take a little sliver here. A very small sliver of this rod that has a width dx. And we can say that inside this sliver here, there's just a little amount of q. And the dq will always come from lambda times dx. Dimensional analysis should prove that to you here because lambda has units of coulombs per meter. And if we multiply by dx, which has units of meters, we'll just get coulombs here. So inside this little sliver, there's a little bit amount of charge, dq. And what that dq is going to do is it's going to cause an electric field line to go through this point, just like it always does here. Of course, the electric field that's caused by this dq goes in all directions in space, but one direction it goes is right through that point of interest right there. So right there, we're going to call that a little dE. So this dq that's in this sliver here causes a differential electric field called dE to pass through that point. And that's what we're interested in. Now, one thing about these problems here is this is only one representative point. I could very easily draw another little sliver over here and picture its electric field contribution, another little sliver right here, picture its electric field contribution, a sliver way over here, picture its electric field contribution. It doesn't matter what sliver I choose, but ultimately when we add them all together, we will add the contribution to all these slivers together into the dE. So at this point in the game, I'm just going to choose this sliver right here, which is distance x from the axis right here. It could be anywhere, but in this case here, I'm just choosing this general case here, which is distance x from the axis. Let's see what we get. So of course, what we discussed in that previous video about discretizing the problem here is we're going to start with dE is k times dq over r squared. Looks just like the point charge formula, but it's been put in differential form. Instead of E is kq over r squared, it's dE is k dq over r squared. Now we already have a bit of information here. In particular, we know that dq is lambda dx, so we'll just sort of keep filling this in here. So this will be k times lambda times dx over r squared. Here we go. We'll just keep working on it now. Now what we'll do is do a bit of identification now. Remember that r is the distance from the sliver to the charge of interest. So this is your r right here. And if you look very carefully at the graph here, it looks like r will just come from the Pythagorean theorem. In particular, r is just going to be h squared plus x squared. X is how far I am from the axis. That's this leg over here. It is a right triangle. H is how high the point charge is, the point of interest is up there. So I'll just continue filling this stuff in here. I'll get k lambda dx over h squared plus x squared. So that's what my dE is going to be. Now, one of the problems with here, one of the difficulties is that this dE here is a full vector. In fact, I probably should be a little more explicit about that here. There's a vector with an r hat direction, there's a vector with an r hat, and a vector with an r hat. If you're confused about what the r hat means, check our video list. There's another video that describes sort of in detail what r hat does and how you use it. But I sort of have to stop here. There's nothing incorrect about what I've written here, but I can't do anymore because what I really need, I need components of this here. I need components of this net dE electric field, which is being caused by the dq up there. They're not that hard to find. It's just another vector superposition problem. So let's see what we can do here. It looks like if I draw some legs around this particular right triangle, this dE will have a dEx pointing that way. There's a dEx, and it'll have a dEy pointing up like that. So there's my two components right there. And if I call this angle in here something like alpha, that's going to be the same as this alpha, that angle up in there. So I always need some angle in there so I can resolve my vector components. So I'm just going to continue on down here then and see if I can find. It looks like dEx is the adjacent side. So it looks like over here, dEx is dE times the cosine of alpha. And dEy is going to be dE times the sine of alpha, which is some standard trigonometry because it looks like dEy is the opposite side, dEx is the adjacent side. So I can get a couple of things like that going. Now what I can do is just, I know what dE is right here. The magnitude of dE is this quantity right here. That's my k lambda dx over this. So I'll just go ahead and fill that stuff in. K lambda dx over h squared plus x squared. times the cosine of alpha over here. dEy is equal to k times lambda times dx over h squared plus x squared times the sine of alpha. So I've done my vector projection. I've got my x component here, my y component here, right here, and I'm going to continue down with the work here. But what we'll do next is it turns out that alpha here also depends on x. Let me describe that to you here, the angle. This angle here depends on where the field point is. So if this x is very close to the origin, say like right in here, alpha would be a very large angle. As x gets out here towards the end of the rod, alpha can get starting to get kind of small, because this angle here would be, the angle of this line would be much steeper if alpha was out there. Then the angle would start getting kind of small in there. So alpha depends on some of these parameters. It's not that hard to pull out. For instance, if I just look at this right triangle here, I can see that the cosine of alpha is adjacent over hypotenuse, or it's x over r. But I know what r is. It comes from the Pythagorean theorem over here. So what I can write here is that the cosine of alpha is x over r. But remember, I know what r is. It's the square root of h squared plus x squared. It says so right up there, just using that. Likewise, the sine of alpha comes from this triangle over here. It's opposite over hypotenuse, and the opposite side is that height h right there. So the sine of alpha is h over the square root of h squared plus x squared. See, I've got my two trig components now, or my two vector projection, or my two trig functions written in front of some parameters that are more relevant to the problem. So I'll go ahead and fill all this stuff in. K times lambda times dx over h squared plus x squared. That's just this part here. But now I'm going to multiply by that cosine, which gives me an x over the square root of h squared plus x squared in the bottom right there. Likewise, I'll do the same thing for my dEy down there. Just move the board up a bit so you see what I'm doing here. There's my dEx. Here's that dE in here. There's the dE part copied from up there. And the cosine alpha being this is just written right here. So here's the dE and there's the cosine alpha. Got that all in there. Let's do the same thing for dEy. See if we can fit it in there. So this can be a k lambda times the dx over, I don't have a square root in here, over h squared plus x squared. And then we have the sine of alpha in here, which is going to be h over the square root of h squared plus x squared. Something like that. So again, once again, here's that dE again, and this is your sine of alpha in here. See, I'm just writing it in a different way. Again, same thing over here in the x, there's the dE, here's the cosine of alpha. So we have it all going in there. They look similar, but they're not. They'll have the same denominator. This has an x in the top, that has an h in the top there. So what I'll do now is I'll just sort of try to keep these relations down here. I'll get us a nice clean whiteboard and we'll finish up the problem. Just a few more steps here. Maybe I'll sort of keep the picture up there. I'll just sort of get rid of this. And we'll write our results. So what we have going right now, we have dEx. What I'll do also is when I rewrite these, I'll do a bit of simplification here, because I know when I combine an h squared plus an x squared under the radical here, the exponents add, so I'll get an h squared plus x squared to the 3/2 power for both of them right there. So a bit of simplification. I get a k, a lambda, a dx times x, and in the bottom right here, we get an h squared plus x squared, all that to the 3/2 power. That's what my dx EEX becomes. And my dEy is going to be something similar here. A k lambda dx times h over h squared plus x squared, all that to the 3/2 power. There we go. So these two lines here should be the sort of simplified versions of these, with all the sines and the cosines plugged in and all the exponents added correctly. And these 3/2 powers on these sums here of the h squared plus f squared are pretty common for these problems. So I'll just sort of clear some more space on the whiteboard. So actually the next thing to do now is to recognize that you sort of have all the dependencies tied up here. You've got the sine and the cosine taken out in terms of all the variables here. All you have is, if you look very carefully, what you formed here is your variable of integration is clearly going to be dx. And that's a good thing, because you're going to integrate along the length of the rod, which exists along the x-axis here. And so you have some things that depend on x. So there's an x right there, and there's an x right there, and there's an x right there over here. The h doesn't depend on x. So you have some things that depend on x, other things that don't. But what you recognize now, after you got all this done, is that actually the macroscopic electric field is going to be the integral of dEx. Likewise over here, Ey is just going to be the integral of dEy. So we can do that now. So we can finally find our x component of electric field. It's just, I'll pull all the constants out front. Looks like the k and the lambda can be pulled out front. And the integral you have is x times dx. I'll just reverse the x and the dx over there, over h squared plus x squared to the 3/2 power. Same thing over here. Ey is going to become, I can pull the k and the lambda and the h out in front of the integral because they don't depend on x. And what I'll be left with is the integral of dx over h squared plus x squared to the 3/2 power. And so there you go. These two integrals here are more or less the last steps of the problem. I won't do them here because the video is getting kind of long, but these are the kind of things you should know from your calculus class. You can look in your calculus book, online, use Mathematica, and oftentimes they're so common that they're actually just in the back of your physics book anyway. Let's make sure we're clear on the limits of integration. We're integrating over this variable x, which is the length of the rod. So I'm definitely going to integrate from minus L over 2 to L over 2, and over here, L over 2 to plus L over 2. So if you just do these integrals, somehow you will get some expression for Ex, and you'll get some expression here for Ey. And that should complete the problem for you. Now, if you're so motivated, I don't know what sort of you're shooting for here, or what your professor's asking, or what your problem's asking for here, but of course, once you have Ex and Ey, you can combine them vectorially to find the total electric field, because that's just going to be the square root, once again, of Ex squared plus Ey squared. So there's a couple of things that will happen here, which you can probably notice that maybe we should have pointed out before, but it's good to do now. If you look very carefully at the problem, for every sliver on one side, say x over here, there's going to be a sliver over here, which is a distance minus x from the origin. That's going to produce sort of its electric field that goes this way. There's some symmetry here. So if we look at, here's a dE right here, because of the sliver on the opposite side of the origin from the one that we've analyzed thus far in the problem. If I draw in the vector components of this one, there's going to be one this way and one this way. So what you notice due to symmetry arguments here is that for every dEx on one side of the axis, there's going to be a dEx on the other side of the origin, sort of like a twin or a pair or a cousin, and they're always going to cancel here. So what you conclude is that the x component of the electric field for this line is going to be 0. In other words, if you do this integral right here, you should get 0 for it. That's just a symmetry argument. You can actually prove it with calculus by doing this integral right here, or you could see it from the very onset of the problem. You say, I don't really even need to bother with the Ex because it's just going to cancel through the symmetry. So what will happen here is you'll just get some Ey, and this one here, in general, will not be 0 here. You must get some electric field for that if you're a finite distance from the rod, so it won't be 0 there. So I'll let you crank through all the math, but I do want to conclude this video with just one last look, give you a bit of physical insight into this process, right, into this factor here, that Ex is 0 and Ey is not 0, is that if you have an infinite line like this, it gives you a little intuition about what the electric field is going to look like here. So here's the infinite line like that, or not infinite line, it was a finite line here. It goes from L over 2 to L over 2, minus L over 2, and it's given some charge density lambda. That's the problem that we just worked. All I want to do is just look at the final electric field one last time. There's a point up here. We saw from our result last time that Ex must be 0. Looks like Ey is not equal to 0. So we had sort of those two things going on. We saw that from the calculus. Either the integral is going to be 0, or you can look at the symmetry. So what that means, if you have a line like this, the direction of the electric field is going to be something like this. It's going to point out like that. This is where going to be your total electric field due to the line. And when you put all the math together, you'll actually get an expression for it. It might be in your physics book, or you can certainly find it on the web somewhere. But the point is that this is some just intuition that you can just carry around with you. That if you have a line of charge that has a charge density lambda like that, if lambda is greater than 0, these will be a bunch of positive charges on here, and electric fields always point away from positive charge. In the case of a line, you just get an electric field pointing up like that. So if you have a line right here of charge, the electric field due to this line is going to be like that. If the line looks like this, the electric field is going to be like that. Always at a point here that's sort of midway that bisects the line of that, right over that center point right there. The electric field will always point away from it like that. Now, one reason to think about this is because the only result that you really know right now is the electric field due to a point charge. And you know that for point charges, the electric fields sort of go in this spherically symmetric direction all around like that. In the case of a positive charge, they point away like that. So this is a result that you've been working on for quite some time now. The electric field due to a point charge is this nice circularly symmetric thing. And this is a result here. Sure, no problem with that. But here's another result right here. That if you don't have a point charge, but you have a line of charges, the electric field doesn't look anything like this at all. It now looks just like this, where you just have one single arrow on this bisector point pointing straight away from the line like that. So there's sort of another result for you right there. Bit of intuition. So also just keep in mind that this result, having a singular arrow pointing away like that, is only on the bisector like this here, only on the perpendicular bisector. So don't start getting confused and thinking that we've done anything to address the electric field in this region or this region over here. We have not done that. We've only found the electric field on the perpendicular bisector, which is often about the limit of electric field that you need for a class like this. There's plenty of headache in getting out of the electric field already. We don't need to go off the bisector.